Welcome to Bedtime Universe. Here, every night is a journey across the endless sky. Close your eyes and let the stars whisper their stories. Let's go to the story. The alert came through at 3:47 a.m. Pacific time, a rhythmic chime that pulled Dr. Ilara Vance from the shallow sleep she'd been managing in the observation lounge at the Jet Propulsion Laboratory. Her tablet's screen glowed with the automated notification from the Atlas survey system in Hawaii, a new fast mover with an orbital eccentricity that made her breath catch even before her coffee-deprived brain fully processed the numbers. Eccentricity 1.93. Hyperbolic, decisively hyperbolic. She was moving before conscious thought caught up, her fingers already composing the emergency convocation message to her rapid response team, while her feet carried her down the familiar corridors toward the small body dynamics lab, the fluorescent lights flickering to life in sequence, as motion sensors detected her passage through the pre-dawn stillness. By the time she reached the lab, 3 other astronomers had already materialized, drawn by the same siren call of impossible orbital parameters, their faces illuminated by the blue-white glow of multiple monitors, displaying preliminary trajectory solutions that all pointed to the same extraordinary conclusion. This object, provisionally designated 3I divided by Atlas, had not originated from anywhere within our solar system's gravitational embrace, but had instead fallen toward our Sun from the vast interstellar gulf. Only the 3rd such visitor humanity had definitively identified, and the first since 2I divided by Borisov had departed in 2020. Ilara's colleague Marcus Chen was already running confirmation protocols, his hands dancing across keyboards as he queried every available sky survey database for recovery images, any photographic plate or digital archive that might have captured this traveler before Atlas had flagged it, anything that would extend the orbital arc and tighten the uncertainty ellipse that currently smeared across millions of kilometers of possible positions. The preliminary solution suggested a perihelion distance of just 0.032 astronomical units, less than 1/30th the distance from Earth to the Sun, a trajectory that would bring this interstellar visitor screaming through the solar corona at velocities exceeding 290 kilometers per second relative to the Sun, subjecting whatever material composed its surface to thermal and radiation environments that would vaporize ordinary rock and sublime any volatile ices in spectacular fashion. They had perhaps 6 weeks, maybe 7 if the photometric models held, before 3I divided by Atlas would be lost to them forever. First to the blinding glare of solar conjunction as it passed behind the Sun from Earth's perspective, then to the infinite dark as its hyperbolic orbit carried it back out past the heliopause and into the interstellar medium from which it had emerged. 6 weeks to characterize something that had potentially traveled for millions of years through the frozen desert between stars, carrying within its structure clues to the chemistry and physics of planetary systems so distant their light had not yet reached human eyes, or perhaps carrying something stranger still, though Ilara suppressed that thought with practiced scientific discipline, even as it flickered at the edges of her consciousness. The confirmation came within 18 hours, as observatories across the globe turned their attention to the coordinates Atlas had provided. Each new position measurement, refining the orbital solution until the hyperbolic nature of the trajectory became not just probable, but certain, the systematic deviation from any closed orbit, eliminating the possibility of measurement error or computational artifact. The International Astronomical Union's Minor Planet Center issued the official designation, and suddenly Ilara's team was at the center of a global astronomical effort that reminded her of the frantic weeks following the discovery of Oumuamua. Except this time they had advance warning of the perihelion approach and sophisticated models of interstellar object behavior, informed by 2 previous encounters, though, as she would soon discover, those models would prove woefully inadequate for understanding 3I divided by Atlas. The first spectroscopic observations came from the Very Large Telescope in Chile, where the European Southern Observatory had granted emergency directors discretionary time, bumping scheduled observations to capture the weak reflected sunlight from an object still more than 2 astronomical units distant. Elara stood in the JPL analysis theater with a dozen other scientists, the curved wall displaying the reduced spectrum in high resolution, and felt the familiar thrill of discovery transform into something more complex, a mixture of excitement and unease that she couldn't immediately articulate. The spectrum showed emission lines consistent with outgassing, confirming that 3I divided by Atlas was active like a comet, despite its interstellar origin. But the relative intensities were all wrong. The hydroxyl radical emission, that ubiquitous signature of water sublimation that dominated every cometary spectrum she'd ever analyzed, was strangely muted, barely rising above the noise floor. Instead, the spectrum blazed with carbon monoxide emission, far more CO than should exist relative to water if this object had formed in a protoplanetary disk, even remotely similar to our own. Marcus noted the anomaly first, his voice careful and measured as he highlighted the line ratios on the display, suggesting contamination or instrumental artifact, before allowing himself to consider that the observation might be genuine. But as subsequent observations from Keck and Gemini confirmed the same bizarre composition, the team had to confront the possibility that 3I divided by Atlas represented a genuinely alien chemistry, perhaps an object formed in a stellar system with radically different volatile abundance patterns, or something that had experienced thermal processing during its interstellar journey that preferentially depleted its water content while preserving more refractory species like CO. The photometric campaign revealed additional strangeness that defied easy categorization. Unlike the relatively stable light curve of 2I divided by Borisov, or the dramatic tumbling rotation of Oumuamua, 3I divided by Atlas exhibited irregular brightness variations that seemed almost chaotic, fluctuations of up to 0.7 magnitudes, over timescales ranging from hours to days, with no clear periodicity that would indicate simple rotational modulation of an irregularly shaped body. Elara's graduate student, Yuki Tanaka, spent sleepless nights trying to model the light curve using every combination of shape, albedo variation, and viewing geometry her software could generate, but nothing produced a satisfactory fit to the observations. The object seemed to be changing its cross-sectional area or reflectivity in ways that suggested either an extremely complex shape undergoing precession, active surface processes that altered its reflective properties on short timescales, or some form of mass loss that was more dramatic and variable than typical cometary activity. The latter hypothesis gained support when high-resolution imaging from Hubble, scheduled during a brief gap in the telescope's crowded observation calendar, revealed an asymmetric coma structure that didn't conform to the expected fountain model of dust and gas, expanding radially from a sublimating nucleus. The images showed what appeared to be discrete jets or plumes emanating from specific locations on the rotating body, but their activity patterns didn't correlate with solar heating in any straightforward way. Some jets seemed to activate and deactivate on timescales too short to be explained by thermal inertia, while others persisted through the object's rotation into the night side, where solar radiation should have been insufficient to drive sublimation. Elara found herself presenting these anomalies to an emergency convocation of the Planetary Science Division, her carefully worded analysis, emphasizing the scientific uncertainties while trying to avoid the sensationalist speculation that was already proliferating in various online astronomy forums and tabloid publications. She knew that Oumuamua had spawned endless debates about its potentially artificial nature, arguments that had consumed enormous amounts of professional time and energy while generating more heat than light, and she was determined to keep the investigation of 3I divided by Atlas grounded in rigorous observation and conservative interpretation, even as the object's behavior strained the boundaries of conventional cometary models. But privately, in the quiet hours of early morning when she reviewed the data streams alone in her office, Elara couldn't entirely suppress the recognition that they were observing something genuinely unprecedented, an object whose properties existed in parameter space that no known natural process could easily populate, at least not according to current understanding of small body physics and interstellar medium chemistry. The non-gravitational acceleration complicated everything further. As the orbital solution refined with each passing day of astrometric observations, the trajectory calculations began showing systematic deviations from a purely gravitational path, the telltale signature of rocket-like forces imparted by asymmetric outgassing as volatile material, sublimated from the sunward-facing surface and created thrust through momentum exchange. Such effects were well documented in conventional comets and had been observed in Oumuamua as well, providing a natural explanation for that object's deviation from a Keplerian orbit and removing the need for more exotic hypotheses about solar radiation pressure acting on an artificial light sail. But the magnitude and direction of 3I divided by Atlas's non-gravitational acceleration didn't correlate with the observed outgassing activity in any sensible way. The acceleration vector seemed to lag the subsolar point by an angle that changed over the course of the object's rotation, suggesting either an extremely complex surface distribution of volatile sources or some form of thermal processing that created long-lived hotspots capable of driving sublimation hours after direct solar illumination had ceased. Marcus developed elaborate models incorporating subsurface heat transport, porosity-dependent thermal diffusion, and heterogeneous composition maps, but even his most sophisticated simulations couldn't reproduce the observed acceleration vector without invoking parameter values that existed well outside the range measured for any known cometary nucleus. The team's internal discussions grew increasingly animated as perihelion approached, with Elara finding herself mediating between those who insisted on explaining every anomaly through increasingly contrived natural mechanisms and those who cautiously suggested that they might need to consider hypotheses outside the standard model of small body behavior. The phrase, "we should keep an open mind," became a battlefield, with each side accusing the other of either close-minded conservatism or reckless speculation, depending on which direction the intellectual openness was supposed to extend. Elara tried to steer a middle course, insisting that extraordinary claims required extraordinary evidence, but acknowledging that the evidence they were accumulating was itself becoming rather extraordinary, a collection of anomalies that individually might be dismissed as measurement uncertainty or modeling inadequacy, but collectively painted a picture that didn't quite fit any existing template. The political pressure intensified as media attention focused on the mission, with the JPL director fielding calls from congressional staffers wanting to know whether taxpayer dollars were being used to investigate alien spacecraft, a characterization that made Elara's teeth clench every time she heard it because it fundamentally misrepresented both the team's scientific approach and the nature of the anomalies they were documenting. She drafted carefully worded press releases, emphasizing that all observations remained consistent with a natural object of exotic composition, and that the scientific process required patience and systematic investigation rather than premature conclusions. But she could sense the institutional nervousness about another Oumuamua-style controversy that might damage JPL's reputation for sober scientific analysis. The countdown to perihelion became the organizing principle of her existence, each day bringing the object closer to that blazing closest approach, while simultaneously making observations more difficult. as 3I divided by Atlas's elongation from the Sun decreased and the sky background brightened. The team worked in shifts to maximize telescope time allocation, coordinating observations from facilities around the world to maintain nearly continuous coverage as the object accelerated inward, its heliocentric velocity climbing toward values that made orbital mechanics feel visceral rather than abstract. At 2 astronomical units, they measured rotation periods and refined the spectroscopic inventory of outgassing species. At 1 AU, they detected silicate emission features, indicating dust production, and obtained thermal infrared observations that constrained the nucleus temperature and size. At half an AU, the solar conjunction geometry forced them to rely on spacecraft data, including an audacious proposal to correlate 3I divided by Atlas's trajectory with pointing data from the Parker Solar Probe, which was then engaged in its own death-defying plunges through the solar corona, as part of its mission to study the Sun's outer atmosphere and the acceleration mechanisms of the solar wind. The Parker correlation proposal came from Yuki, who had spent weeks analyzing spacecraft telemetry and realized that one of Parker's perihelion passes would bring it within the same general region of space that 3I divided by Atlas would transit approximately 8 hours earlier, separated by millions of kilometers, but close enough in the vastness of the inner solar system that the probe's instruments might detect enhanced dust or volatile species. If 3I divided by Atlas shed significant material during its closest approach, the idea was technically brilliant and operationally insane, requiring emergency reprogramming of Parker's data collection protocols during a phase of the mission when the spacecraft was already operating at the edge of its thermal tolerances, its heat shield facing the full fury of the solar corona, while its instruments peeked around the shield's edges to sample plasma conditions that no other human-made object had ever survived. The proposal triggered heated debates within NASA's heliophysics division, with mission planners arguing that any alteration to Parker's observation sequence risked compromising primary science objectives and potentially endangering the spacecraft if thermal constraints were violated. But the sheer scientific opportunity represented by 3I divided by Atlas's passage through Parker's observation volume eventually won out, helped by Ilara's impassioned presentation to the mission directorate, emphasizing that this was likely a once-in-a-generation chance to observe an interstellar object under the most extreme conditions imaginable, conditions that would either vaporize it entirely or drive outgassing at rates that would reveal definitive information about its internal composition and structure. The final week before perihelion felt like existing in a permanent state of controlled chaos, with Ilara sleeping in her office when she slept at all, sustained by caffeine and the electric anticipation of imminent discovery. The last direct Earth-based observations came from the Solar Dynamics Observatory, which managed to capture 3I divided by Atlas as a dark speck transiting the solar disk during a brief window when the geometry permitted, the object's silhouette providing one last astrometric data point before it plunged into the observational blind zone created by solar glare. The transit images showed an elongated profile, consistent with either a highly irregular shape or possibly a bifurcated structure that suggested the object might be a contact binary, 2 lobes of material held together by tenuous gravitational attraction, though the resolution was insufficient for definitive morphological conclusions. Then came the waiting, 37 hours of near-complete observational blackout, while 3I divided by Atlas made its closest approach to the Sun at a distance of 4.8 million kilometers, plunging through regions where the ambient temperature exceeded 2000 Kelvin, and the solar wind density was more than 1,000 times its value at Earth's orbit, an environment so hostile that no spacecraft had ever operated successfully within it, except Parker and the earlier Helios probes with their specialized thermal protection systems. Ilara tried to occupy herself with data analysis and paper writing, but found her attention constantly drifting back to the countdown timer she'd set up on her secondary monitor, watching the minutes tick down to Parker's scheduled observation window. When the spacecraft would execute its own perihelion passage and begin searching for any trace of 3I divided by Atlas's passage through that inferno. The Parker data arrived in compressed bursts as the spacecraft emerged from behind the Sun and re-established contact with the Deep Space Network. The telemetry first, confirming that the spacecraft had survived its close approach, with all systems nominal, then beginning to downlink the science observations that would take hours to fully transfer given the spacecraft's distance and the limited bandwidth of its high-gain antenna. Ilara's team gathered in the mission support area, watching the progress bars slowly fill as gigabytes of detector data made their way across 150 million kilometers of space at the speed of light. Each completed file immediately fed into the automated processing pipeline that would calibrate and reduce the raw observations into usable scientific measurements. The first indication that something remarkable had occurred came from the Solar Probe Cup instrument, which measured the flux and composition of solar wind plasma flowing past the spacecraft during its perihelion passage. The nominal solar wind parameters showed the expected variations as Parker traversed different magnetic structures in the corona, but embedded within that data stream was a brief, anomalous interval lasting approximately 90 seconds, where the particle flux exhibited unusual enhancement in both density and temperature, accompanied by a compositional spike in carbon monoxide and other volatile species that had no business existing in the solar corona in those abundances. The timing and location of the enhancement matched almost perfectly with where 3I divided by Atlas should have been 8 hours earlier, assuming the object's predicted trajectory remained accurate, suggesting that Parker had flown through the residual wake of material shed by the interstellar visitor during its closest approach, a tenuous stream of gas and dust that had been stretched along the orbit by differential solar wind drag and was now dispersing into the corona. Marcus immediately began modeling the dispersion dynamics, trying to back-calculate the mass loss rate required to produce the observed enhancement, and arrived at numbers that seemed absurdly high, suggesting that 3I divided by Atlas had shed something like 5 to 10% of its total mass during that single perihelion passage, a fragmentation event more dramatic than any previously observed, cometary outburst and reminiscent of the catastrophic disruption events, seen occasionally when sun-grazing comets failed to survive their close encounters with solar heating. But the wide-field imager for solar probe data told a different and more perplexing story. The high-resolution imagery captured during the observation window showed no sign of catastrophic fragmentation or diffuse debris clouds that would indicate complete disruption of the nucleus. Instead, the images revealed what appeared to be an intact object, still maintaining structural coherence, despite having just survived temperatures and radiation fluxes that should have vaporized most known materials. The photometric analysis showed that 3I divided by Atlas was significantly fainter than it had been during the final Earth-based observations, consistent with substantial mass loss. But the morphology remained relatively compact rather than diffuse, suggesting that whatever had been shed during perihelion passage had been lost in discrete events rather than through continuous erosive ablation. And there, embedded in the highest resolution frames, was the feature that would ultimately define the entire mission and generate debates that would continue for years afterward. A geometric regularity to the object's brightness distribution that didn't match any natural surface texture pattern, a series of what appeared to be planar facets reflecting sunlight at angles that suggested either crystalline structure or something more deliberately organized. The imagery right at the threshold of resolution where definitive interpretation became impossible, but suggestive patterns tantalized the imagination. Alara stared at the enhanced images for hours, rotating them through different contrast stretches and filtering algorithms, trying to determine whether the apparent geometry was real or merely an artifact of image processing and human pattern recognition bias. That cognitive tendency to see order in randomness that had plagued astronomical interpretation since ancient astronomers saw animal shapes in random stellar configurations. She convened 3 separate independent analysis sessions, where different team members examined the data without prior exposure to each other's interpretations, trying to establish whether the geometric features were consistently detectable across different analysis methodologies or dissolved into noise when examined with sufficient rigor. The results were maddeningly ambiguous, with some analysis chains clearly showing the planar features, while others reduced them to statistical insignificance, depending on the specific pre-processing steps and enhancement algorithms applied. Marcus argued passionately that they were seeing crystalline structure, that 3I divided by Atlas might be composed partially of exotic high-temperature materials like graphite or silicon carbide that could form macroscopic crystallites under the right conditions, creating large-scale facets that would reflect light coherently and produce the geometric patterns in the imagery. It was an elegant hypothesis that explained the object's survival of perihelion heating while accounting for the unusual geometric features. And Alara wanted to believe it because it preserved the natural origin interpretation while acknowledging the genuinely anomalous observations. But Yuki quietly pointed out that the facet orientations, if they were real, didn't correspond to any obvious crystallographic symmetry that would emerge from natural crystal growth processes, and that the distribution of bright facets seemed to show preferential orientation toward the sun in a way that suggested functionality rather than accident. Though she emphasized that this observation was highly preliminary and might not survive more rigorous geometric analysis. The team's final report, submitted to science and released simultaneously to the astronomical community and the press, walked an intellectual tightrope that Alara knew would satisfy no one completely, while hopefully avoiding the worst excesses of either premature certainty or sensationalist speculation. They documented the extraordinary properties of 3I divided by Atlas comprehensively. The anomalous volatile composition dominated by carbon monoxide rather than water, the irregular light curve variations that defied conventional rotational modeling, the non-gravitational acceleration vector that didn't correlate simply with observed outgassing, the survival of extreme perihelion conditions that should have destroyed a conventional cometary nucleus, and the geometric features tentatively detected in the Parker Solar Probe imagery that might indicate large-scale crystalline structure, or possibly something more organized, with the critical caveat that the resolution limits made definitive interpretation impossible. Their conclusion emphasized that while all observations could potentially be explained by a natural object with exotic but not impossible properties, the collection of anomalies placed 3I divided by Atlas in a genuinely unique position within the taxonomy of small bodies, representing either an interstellar object formed under radically different conditions than those that prevailed in our own solar system's protoplanetary disk, or possibly an example of a formation mechanism or evolutionary pathway that remained poorly understood within current planetary science paradigms. The phrase that would be quoted and debated endlessly appeared near the end of the discussion section, the result of 3 hours of team wordsmithing to capture their genuinely uncertain epistemic state. We cannot exclude the possibility that 3I divided by Atlas represents an engineered object, or at least an object whose properties reflect processes not currently encompassed by our understanding of natural small body formation and process. Evolution, though we emphasize that this conclusion emerges not from any single definitive observation, but from the cumulative weight of multiple anomalies that collectively strain conventional explanatory frameworks. The media response was predictable and frustrating in equal measure, with headlines ranging from "Scientists confirm alien probe visited solar system" to "JPL team debunks latest interstellar UFO hysteria." Neither characterization capturing the carefully calibrated uncertainty team had tried to convey. Elara found herself giving dozens of interviews, repeatedly explaining the difference between acknowledging the limitations of current understanding and making positive claims about alien technology, emphasizing that science advanced through exactly this kind of encounter with anomalous data that didn't fit existing models, that the point wasn't whether 3i divided by Atlas was natural or artificial, but rather what its properties could teach us about the diversity of possible outcomes in planetary system formation and evolution. Some of her colleagues criticized the team for even mentioning the possibility of engineered origins, arguing that such speculation gave legitimacy to fringe theories and undermined public confidence in scientific rigor. Others criticized them for not going far enough, for hedging their conclusions with so many caveats that the genuinely extraordinary nature of the observations got buried in scientific caution. Elara defended their approach as honest reporting of genuine uncertainty, noting that the data simply didn't support strong conclusions in either direction, and that pretending otherwise would be more damaging to scientific credibility than acknowledging the limits of current knowledge. In the months following perihelion, as 3i divided by Atlas receded back into the outer solar system and eventually beyond the reach of even the most sensitive telescopes, Elara and her team continued analyzing the archived observations, publishing detailed follow-up papers on specific aspects of the object's behavior and refining their models with the benefit of more time for careful analysis. The geometric features in the Parker imagery remained controversial, with some analysts claiming to detect additional evidence of structure in reprocessed data, while others argued that the features dissolved into noise when proper statistical corrections were applied. Several theoretical papers appeared proposing various natural mechanisms for 3i divided by Atlas's anomalous properties, invoking exotic ice compositions, complex thermal differentiation processes, or formation in unusual stellar environments, each model explaining some subset of the observations while struggling with others. The debate continued in scientific conferences and journal pages, a productive uncertainty that drove new theoretical work on interstellar object properties and motivated proposals for future missions capable of closer encounters or even sample return from the next interstellar visitor that graced the prude inner solar system with its presence. Elara found herself strangely content with the ambiguity, recognizing that the question of 3i divided by Atlas's nature might remain genuinely unresolved for decades or longer until either additional interstellar objects provided comparative context or technological advances permitted observations currently beyond reach. She thought about the object sometimes during quiet moments, imagining it rushing outward through the heliopause and back into the interstellar medium, carrying its secrets with it into the vast dark between stars, perhaps to be studied again by other civilizations orbiting other suns in the distant future, or perhaps to travel forever unobserved through the cosmic void, a mystery that would remain forever beyond human reach. The experience had taught her something about the nature of scientific understanding, that there existed a space between knowledge and ignorance, where honest uncertainty was not just acceptable but essential, where the proper response to genuinely anomalous data was neither premature certainty nor reflexive dismissal, but rather sustained engagement with the unknown, a willingness to sit with discomfort and allow mysteries to remain mysterious until time and better observations revealed clearer answers. She kept one of the enhanced Parker images on her office wall, that tantalizing glimpse of geometric patterns that might be crystalline facets, or might be artifacts, or might be something stranger still. A reminder that the universe remained fundamentally mysterious despite centuries of scientific progress. That there existed phenomena at the edges of human experience that defied easy categorization, and that the proper response to mystery was not to prematurely resolve it through convenient assumptions, but rather to approach it with humility, rigor, and wonder, acknowledging that some questions might not have simple answers, and that the pursuit of understanding was often more valuable than any particular conclusion. Years later, when other interstellar objects were detected and studied, providing comparative context for 3I divided by Atlas's anomalous properties, the scientific consensus would gradually shift toward recognizing it as an extreme example of natural diversity rather than evidence of artificial origin. Though a minority of researchers continued to argue that certain features remained inadequately explained by conventional models. But on that evening, when the final data was compiled and the last papers submitted, Ilara stood on the JPL campus under the California stars, looking up at the sky that held mysteries beyond counting, and felt profoundly grateful to have been present for this encounter with the genuinely unknown, this moment when humanity had briefly touched something that had traveled between the stars and found itself unable to fully comprehend what it had encountered, a reminder of how much remained to be discovered and how far we still had to go before claiming any complete understanding of the cosmic environment we inhabited. Welcome to Bedtime Universe, when the world grows quiet and the city lights fade beneath the curtain of night. We turn our eyes toward the endless sky, a canvas painted with mysteries older than time itself. Here, every star you see might already be gone, yet its light still travels across the darkness, whispering stories from millions of years ago. From wherever you're watching this, maybe lying in bed, staring at your ceiling, or sitting by the window, wondering what's beyond those stars, know that right now, you're part of something vast, something beautiful, something that connects us all. So, take a deep breath. Let your mind drift, because tonight, we'll journey beyond the familiar sky, exploring one more secret of the cosmos together. This is Bedtime Universe. And now, let's begin our story. Right now, 19 million miles above the Martian surface, something is passing by that shouldn't exist. Not here. Not moving at 210,000 kilometers per hour. Not outgassing like a comet, while barely being pushed by its own jets. 3 Atlas, the third confirmed visitor from another star system, is making its closest approach to Mars tonight. And every spacecraft we have up there is watching. There's a 60/40 split among those brave enough to guess. 60% say it's natural. 40% won't rule out that it was built. The chemistry is wrong. Belching carbon dioxide at 8 times the rate of water, a ratio so bizarre it sits 6 standard deviations outside normal. The size doesn't add up with estimates ranging from 300 meters to 5 kilometers. And the statistics? Well, finding an object this massive as only our third interstellar detection makes some people very uncomfortable. 3 hypotheses, 1 passing visitor. Tonight's data could settle this, or it could make everything stranger. What are Mars orbiters seeing right now as this thing blazes past? What will Hubble catch at perihelion in 3 weeks? And if the numbers still don't add up after tonight, what does that mean for what we think we know about the cosmos? Before we dive into what's actually happening up there, hit subscribe and tell me in the comments where you're watching from tonight. I'd also love to hear your thoughts. Do you think we're alone in observing this, or is there someone else out there watching? Part 1. The flyby that will shock the world. Tonight, October the 3rd, 2025. Right now, as you're hearing these words, Something ancient and foreign is screaming past Mars at over 210,000 kilometers per hour. Its name is 3I Atlas, and it's about to get closer to the red planet than most of us will ever get to understanding what it actually is. Multiple spacecraft orbiting Mars have their instruments trained on this visitor, and for good reason. This isn't just another comet. This is the third confirmed interstellar object to pass through our solar system in recorded history, and it's behaving in ways that make astronomers deeply uncomfortable. Let me set the table. In 2017, something called Oumuamua zipped through our neighborhood and left everyone scratching their heads. It accelerated in ways comets aren't supposed to. Looked like a cigar or a pancake, depending on who you asked, and vanished before we could get a proper look. Then came Twee Boris in 2019, which was refreshingly normal. A comet that looked like a comet, acted like a comet, had a nice visible coma of gas and dust, and didn't keep anyone up at night. We breathed a collective sigh of relief. The universe made sense again. Then July 1st, 2025 happened. The Atlas survey, which is basically humanity's early warning system for things that might kill us or just really confuse us, spotted something new. Something moving wrong. Not wrong like broken, but wrong like it doesn't belong here. The orbit was hyperbolic, meaning it's not gravitationally bound to our Sunday. It came from somewhere else out there in the galactic dark, and it's just passing through. We named it 3 Atlas. The I standing for interstellar, 'cause apparently we've reached the point in human history where we need a naming convention for visitors from other star systems. Now, here's where it gets interesting. Hubble Space Telescope observations put an upper eyes limit on this thing's nucleus, at around 5.6 kilometers across. That's already substantial. For context, that's roughly the size of the asteroid that wiped out the dinosaurs. But here's the catch. It could be much, much smaller. The estimates range down to maybe just 320 to 440 meters. That's a massive error bar. And the reason is simple. We can't see the nucleus directly. It's shrouded in a coma, a cloud of gas and dust that's making it appear larger than it actually is. So, we're flying somewhat blind, which is never ideal when you're trying to figure out if something is natural or not. But size isn't the only puzzle. There's this thing called non-gravitational acceleration. When comets heat up near the sun, they release gases, and those gases push the comet around like tiny rocket thrusters. It's subtle, but it's measurable. MUA had this acceleration, and it was weird because we couldn't see any coma to explain it. That's partly why some people started wondering if it might be artificial. 3 Atlas, on the other hand, has a very clear, very active coma. JUICE, the James Webb Space Telescope, has seen it outgassing like crazy, and yet the non-gravitational acceleration is incredibly weak, almost negligible. The dynamics suggest something with a minimum mass of about 33 billion tons and a diameter of at least 5 kilometers if we trust the outgassing numbers JWST is giving us. That's heavy. That's really heavy for something that might be under 6 kilometers across. The math isn't adding up neatly, and when the math doesn't add up in astronomy, that's when people start proposing alternatives. Tonight, 3IE Atlas is passing about 18 to 19 million miles from Mars. That's roughly 29 to 30 million km, if you prefer metric. In December, it'll make its closest approach to Earth at around 269 million km. So, to be absolutely clear, there is zero threat to our planet. None. But this Mars encounter is critical because it's our best chance to study this thing up close. Mars has multiple spacecraft with sophisticated instruments in orbit right now, and they're all watching. This is essentially a cosmic drive-by, and we've got front row seats. The chemistry alone is enough to make you pause. JWST detected a carbon dioxide-dominated coma with a CO2 to H2O ratio of about 8:1. That's among the highest ever measured for any comet anywhere. Most comets are water-rich. Water ice is the dominant volatile, but this thing, it's belching out carbon dioxide like it's trying to terraform Mars in reverse. Along with the CO2, they found water, carbon monoxide, carbonyl sulfide, and water ice particles. But the ratios are all wrong. It's like finding a bird that quacks, has feathers, waddles like a duck but tastes like beef. Technically possible, but you'd want to double-check your taxonomy. And then there's Aviv. For those unfamiliar, Lo is a Harvard astrophysicist who's made a second career out of not dismissing the possibility that some of these interstellar objects might be artificial. He proposed a light sail explanation for Oumuamu's acceleration, and while most of his colleagues remain unconvinced, he's now turned his attention to 3 Atlas. He's even created something called the Loeb scale, a 0 to 10 ranking system for how likely an object is to be extraterrestrial technology. 0 means definitely natural. 10 means confirmed alien and possibly dangerous. In early August, some commentary attributed a rating of 6 out of 10 to 3I Atlas. That's a 60% confidence level that this thing might be technological. Later in his own Medium post, as more data came in, Lo adjusted it down to 4 out of 10. Still elevated. Still not dismissing the possibility. And that number, whether you agree with the framework or not, has ignited a firestorm of debate. So, we're left with 3 competing narratives as the Mars spacecraft track this object through their sensors tonight. First, the orthodox view. It's a comet. A weird comet. An exotic comet with unusual chemistry, but ultimately just a natural refugee from another star system. Second, the artifact hypothesis. It's something built, something sent, something that might be watching us right now as we watch it. And third, a scenario that somehow manages to be both less fantastical and more terrifying. It's a fragment, a shard from something that was destroyed far away, billions of kilometers from any star, and it's part of a debris stream that we're only just beginning to encounter. If the coma we're seeing is real outgassing, why is the push from that gas so weak? Why is the chemistry so skewed? Why now? Why 3 objects in 8 years, when we've been looking at the sky for centuries? Tonight, as 3 Atlas passes Mars, we might start getting answers, or we might just get better questions. Part 2, Data from Mars, the Silent Witnesses. Let's talk about what's actually happening up there right now. The European Space Agency has 2 spacecraft in Mars orbit that are perfectly positioned for this encounter. Mars Express, which has been studying the red planet since 2003, and the ExoMars Trace Gas Orbiter, a newer addition launched in 2016. Both are slated to monitor 3 Atlas from October 1st through October 7th, with the closest geometry occurring today, October 3rd. And this isn't just a lucky coincidence. Mars orbit is an absolutely killer vantage point for this observation. And here's why. When you're trying to observe something moving at interstellar velocities, every angle matters. From Earth, we're looking at 3I Atlas from one perspective. From Mars, which is currently about 225 million kilometers away from us, depending on where both planets are in their orbits, we get a completely different viewing angle. It's like the difference between seeing a car drive past you on the street versus watching it from a drone overhead. The geometry reveals things that a single viewpoint simply can't. Comet, jet, rotational characteristics. All of these become clearer when you have multiple observation points spread across millions of kilometers of space. So what exactly are these Mars orbiters trying to measure? Let's break it down in terms that don't require a PhD. First, spectra. That's the breakdown of light into its component wavelengths, which tells us what gases are present in the coma. Different molecules absorb and emit light at specific wavelengths. So, by looking at the spectrum, we can identify what's outgassing from the nucleus. JWST already did this in infrared, finding that bizarre carbon dioxide dominance. The Mars instruments will be checking if that signature holds steady, or if it's evolving as the object moves through different heating regimes. Second, reflectivity, or albedo. This tells us what percentage of sunlight the object reflects versus absorbs. A very dark object might be carbonaceous, rich in organic compounds like a burnt marshmallow floating through space. A brighter object might be icy, more pristine. The albedo can give us clues about surface composition and whether there's been radiation processing of the surface materials over millions of years in interstellar space. Third, rotational flicker. If the object is tumbling or spinning, its brightness will change periodically as different faces point toward us. The pattern of that flicker, the light curve, can tell us about the shape. Is it spherical, elongated, irregular? And more importantly, is it rotating in a simple, predictable way? Or is it tumbling chaotically like something that's been through trauma? Fourth, coma shape. Gas doesn't just puff off a comet uniformly in all directions. There are jets, focus streams of material that erupt from specific locations on the surface where the ice is most exposed or where subsurface pressure builds up. JWST already reported that the coma is asymmetrically shaped. The Mars orbiters can track how that asymmetry evolves as the solar heating angle changes. If the jets are natural, they should respond predictably to sunlight. If they're not responding as expected, well, that opens doors. And fifth, jetting behavior. Comets can have outbursts, sudden increases in activity that happen when a pocket of trapped volatiles suddenly breaches the surface. These can be triggered by thermal stress, rotational forces, or impacts from smaller particles. Monitoring for outbursts or the lack thereof gives us insight into the internal structure. But here's the gotcha. Even at closest approach tonight, 3I Atlas is still incredibly far away from Mars by observational standards. We're talking tens of millions of kilometres. The object itself might be only a few kilometres across, possibly smaller, and it's surrounded by a diffuse coma. It's faint. And the Mars orbiters have limited pointing time because they're primarily designed to study Mars, not passing interstellar visitors. So if the orbiters don't see something, that doesn't necessarily mean nothing is there. It might just mean the signal is too weak, or the timing didn't line up. This is why combining perspectives is so critical. Hubble gives us resolution. It can separate the nucleus from the inner coma better than almost anything else we have. JWST gives us chemistry. Its infrared instruments are exquisitely sensitive to the molecular fingerprints of gases. The Mars orbiters give us geometry changes over short timescales. Put all three together, and you start constraining the models. A model that fits Hubble's size limits, but contradicts JUST's chemistry, can be thrown out. A model that explains JUST's carbon dioxide ratio, but predicts a coma shape different from what Mars Express sees, also questionable. Science works by triangulation, and we're setting up a pretty good triangle here. Now, what would anomalies actually look like in this data? Imagine an unexpected flicker pattern, something that doesn't match a simple rotation. That could suggest a complex irregular shape, which might be natural, but would definitely be interesting. Or an off-axis jet, one that's firing in a direction that doesn't make sense given the solar heating geometry. That could indicate subsurface structure. Or if you're feeling speculative, intentional maneuvering or time-variable brightness that's independent of the solar angle. Natural brightness changes follow the Sunday. If something is getting brighter or dimmer for reasons unrelated to how much sunlight it's receiving, that's harder to explain. There's also been some chatter about whether NASA's Mars Reconnaissance Orbiter might attempt imaging with its high-rise camera, which is absurdly high resolution by planetary science standards. But I want to be careful here. As of now, there's no official confirmation that high-rise will be tasked with this observation. It's possible. It's even plausible given the scientific value, but I can't claim it's happening unless an agency confirms it. So, file that under Watch This Space. Looking further ahead, there's another player in this game that most people aren't talking about yet. JUICE mission. JUICE launched in 2023 and is currently on its way to Jupiter, where it'll study the icy moons. But right now, it's in an interesting position geometrically. Later in 3I Atlas's trajectory, JUICE could potentially offer another long baseline observation from a completely different part of the solar system. That kind of multi-point observation spread over weeks or months is how you really nail down an orbit and detect subtle changes. But let's manage expectations. First, public images or spectra from tonight's Mars pass might not arrive for days or even weeks. There's a whole pipeline. Raw data comes down from the spacecraft. It gets calibrated to remove instrumental artifacts. It gets processed to enhance signal to noise. Teams write it up. Peer review happens, or at least internal validation. Then maybe it goes to press or gets posted as a preprint. This is normal. This is how science works. It's not sinister, it's just methodical. So, if you're expecting a press conference tomorrow morning with smoking gun evidence one way or another, temper that hope. What we can expect eventually is a much clearer picture of what 3I Atlas is doing at this critical moment in its trajectory. And that picture will feed directly into the next big question. What is this thing actually made of? Part 3. Anatomy of 3E Atlas. Let's get into the physical reality of this object as best we understand it, which I'll warn you up front is not very well. The size envelope is frustratingly wide. Hubble observations put the nucleus upper limit at approximately 5.6 kilometers across. But because the coma is so active and bright, the actual nucleus could be significantly smaller. Some estimates go as low as 320 to 440 meters. That's a factor of 10 uncertainty in diameter, which translates to a factor of 1,000 uncertainty in volume. If this were a murder investigation, we'd be saying the suspect is somewhere between 5'2" and 6'8". Not exactly a tight description. The reason for this uncertainty is straightforward. We're not seeing the nucleus directly. We're seeing sunlight scattering off gas and dust particles in the coma, and the nucleus is hiding somewhere in the middle of that glow. It's like trying to see a pebble at the bottom of a turbulent, muddy river. You know it's there because physics says it has to be, but you can't measure it directly. Now, here's where things get genuinely peculiar. There's a recent dynamics paper that analyzes the object's trajectory with exquisite precision, using astrometry from observatories all over the world. Amateur astronomers, professional facilities, everyone contributed position measurements. When you track something over months and fit an orbit to all those data points, you can detect incredibly subtle deviations from a pure gravitational path. Those deviations, the non-gravitational accelerations, tell you how much push the outgassing is providing. For 3I Atlas, that acceleration is about 3 times 10^10 astronomical units per day squared. That's a genuinely tiny number. For comparison, many active comets show non-gravitational accelerations orders of magnitude larger. But here's the puzzle. If you know the acceleration, and you know the outgassing rate from JWST's observations, you can back calculate the minimum mass. And the numbers say this thing has to be at least 33 billion tons. Assuming a reasonable density for cometary material, somewhere around 500 kilograms, that implies a diameter of at least 5 kilometers. Notice anything? That's right at the upper end of Hubble's size constraint. So either this thing is genuinely large and massive, or the assumptions going into the mass estimate are wrong. Maybe the outgassing isn't as symmetric as the models assume. Maybe there's something about the compositional structure that makes the acceleration weirdly inefficient. Or maybe, and this is the uncomfortable maybe, it's not a comet at all. Let's talk chemistry, because that's where 3 Atlas really stands out. JWST's NEPS instrument observed the coma on August 6, 2025, and found a carbon dioxide to water ratio of about 8:1. To put that in context, most solar system comets observed at similar distances from the Sun show water as the dominant volatile, often by a large margin. A typical ratio might be closer to 1 part CO, 2 to 10 or 20 parts water. 3I Atlas has flipped that on its head. It's producing 8 times more carbon dioxide than water. Along with the CO2 and H2O, they also detected carbon monoxide, carbonyl sulfide, and water ice grains. The whole cocktail is there, but the proportions are bizarre. What could cause this? One possibility is formation environment. In a protoplanetary disk, the temperature drops as you move away from the star, and different ices condense out at different distances. Water ice forms relatively close in. Carbon dioxide and carbon monoxide ices form further out where it's colder. If 3I Atlas formed near what's called the CO2 ice line in its birth system, it might naturally be enriched in carbon dioxide relative to water. That's a reasonable natural explanation. Another possibility is radiation processing. Imagine this object has been drifting through interstellar space for millions of years, bombarded by cosmic rays and ultraviolet light from distant stars. That radiation can alter surface chemistry, breaking molecular bonds and creating new compounds. It can also create an insulating crust that traps more volatile materials underneath. If the crust preferentially seals in water ice, but allows carbon dioxide to escape more easily, you'd get exactly the kind of skewed outing ratio we're seeing. Again, natural, but exotic. The trajectory itself is unambiguous. This is a hyperbolic orbit, meaning the object is moving faster than escape velocity for the solar system. There's no bound path. It came from interstellar space. It's swinging past the Sun, and it's heading back out into the dark. Perihelion, the closest point to the Sun, happens around October 30th, 2025, at a distance of about 1.4 astronomical units. That's just outside Earth's orbit, closer to the Sun than Mars, but further than Venus. At perihelion, solar heating will be at its maximum. So, if there's going to be any dramatic change in activity or any weird behavior, that's when we'd expect to see it. The speed is worth emphasizing again, 210,000 kilometers per hour, or about 130,000 miles per hour. That's roughly 58 kilometers per second. For context, Voyager 1, the fastest human-made object currently leaving the solar system, is moving at about 17 kilometers per second relative to the Sunday 3-2 Atlas, is more than 3 times faster. That velocity is a combination of its initial interstellar drift speed plus gravitational acceleration as it fell toward the Sunday. And it's that speed, combined with the orbital inclination, that proves beyond any doubt that this thing didn't originate here. Now, let's compare this to baseline comet behavior. Most comets in our solar system, even the long-period ones coming from the cloud, show stronger water dominance when they're active. The carbon dioxide to water ratio typically increases only at very large distances from the sun where water ice is too cold to sublimate efficiently. But CO2, which is more volatile, can still outgas. But 3IU Atlas is active relatively close to the sun and still maintaining that weird ratio. It's sitting way off the normal trend, about 6 standard deviations above typical values. In statistics, 6 sigma is where you start questioning whether your measurement is even from the same population. It's an outlier among outliers. And then there's the acceleration paradox. Outgassing should push the comet around. JWST sees plenty of outgassing, but the actual measured push is tiny. How do you reconcile that? One explanation is balanced jets. If the nucleus is venting material from multiple locations, and those jets roughly cancel each other out in terms of net force, you'd see lots of activity, but minimal acceleration. It's like having 4 rocket thrusters firing in a square pattern, all with equal strength. The object would shake, but it wouldn't move. That's plausible. That's actually fairly common for some comets. But it requires a specific geometry and symmetry that we haven't confirmed yet. The alternative reading is that the object is just really massive, and the gas production, while visually impressive, isn't enough to significantly alter its trajectory. Think of trying to push a boulder with a leaf blower. Lots of air moving, minimal effect on the rock. If 3I Atlas is legitimately 5 kilometers across with a solid interior, the outgassing might simply be too weak to measurably accelerate it. That works mathematically, but it also means this thing is a beast. And finding a 5 kilometers interstellar object so early in our survey history would be, statistically speaking, weird. We'll get into why that's weird when we talk about the mothership hypothesis. So where does this leave us anatomically? We've got something between 300 meters and 5.6 kilometers across. It's surrounded by an active asymmetric coma rich in carbon dioxide. It's moving on a clear interstellar trajectory at absurd speed. Its outgassing chemistry is off the charts abnormal. And despite all that activity, it's barely being pushed around by its own jets. Every measurement we take seems to add a new layer of strangeness instead of clarifying the picture. And that strangeness is exactly what makes some people wonder if we're measuring the wrong thing entirely. Part 4. The Loeb scale and the 60% verdict. All right, let's address the elephant in the telescope. Avi Loeb, chair of Harvard's Astronomy Department, former chair of the Board on Physics and Astronomy of the National Mies, has proposed a framework for quantifying how likely an interstellar object might be artificial. He calls it the Loeb scale, and it runs from 0 to 10. 0 means definitively natural, a rock or a comet with no possibility of technological origin. 10 means confirmed extraterrestrial technology and potentially dangerous. It's deliberately modeled after scales we already use for other existential risks, like the Torino scale for asteroid impacts or the RTER scale for earthquakes. The idea is to give researchers, media, and the public a common language for discussing something that's historically been either dismissed outright or sensationalized beyond recognition. In early August 2025, some public commentary attributed a rating of 6 out of 10 to 3I Atlas under this framework. That's a 60% confidence level that this object might be technological in origin. Later in his own Medium posts, as more data accumulated, particularly the JWST chemistry results, Lowe revised that rating down to 4 out of 10 or 40%. That's still elevated. That's still saying there's a non-trivial chance this isn't just a space rock. And predictably, that claim has set off a debate that split the astronomy community down the middle. So, what pushes the score up? Let's walk through Lowe's reasoning, which, whether you agree with it or not, is methodical. First, size rarity. If 3 Atlas is genuinely 5 kilometers or larger, as the dynamics and mass estimates suggest, that's unusual. Most objects we detect drifting through interstellar space should be small because small objects are exponentially more numerous than large ones. Finding a dinosaur killer-sized chunk so early in our survey history, when we've only confirmed 2 previous interstellar visitors, strikes Loeb as statistically improbable. It's like winning the lottery on your 3rd ticket. Possible, sure, but suspicious. Second, the weak, non-gravitational acceleration despite obvious activity. If you're outgassing enough material to create a visible coma that shows up in JWST spectra, you should be getting pushed around. The fact that the push is so minimal despite the activity suggests either an unusually massive object or a thrust profile that's somehow compensating. Lowe notes that both scenarios are possible naturally, but they're also consistent with a large, solid artifact that's venting something for reasons unrelated to thermal sublimation. Third, the chemistry that 8:1 carbon dioxide to water ratio is genuinely odd. While there are natural explanations, as we've discussed, it's also true that if you were designing a propulsion system for an interstellar probe, you might prioritize volatiles based on efficiency and storage, rather than what's cosmically abundant. Carbon dioxide sublimates at higher temperatures than water ice, so it might be easier to store and control over millions of years in space. This is speculative, obviously, but it's the kind of detail that makes Lowe's antenna twitch. Now, what pushes the score down? First and foremost, the coma itself. JWST sees clear spectral signatures of natural volatiles: water, carbon dioxide, carbon monoxide, carbon sulfide, and water ice, grains. This is chemistry you'd expect from a comet. There's no hint of industrial compounds, no unusual isotopic ratios that might suggest artificial synthesis, no narrow band emissions that could be leakage from electronics. The object is outgassing in a way that's consistent with solar heating and sublimation. That's a strong point in favor of the natural hypothesis. Second, no clear maneuvers. If this were a functioning spacecraft, you'd expect to see deliberate course corrections, acceleration or deceleration that's inconsistent with gravitational forces and outgassing. So far, 3-2 Atlas's trajectory is entirely consistent with a ballistic path. Gravity plus minimal rocket effect from the coma. There's no evidence of active control. Third, the arrival geometry isn't particularly suspicious. Some people have speculated that if an alien probe wanted to study the solar system, it might come in at an unusual angle to avoid detection or to maximize observation time. 3 Atlas's orbit is inclined, but that's normal for interstellar objects. They're not on the ecliptic plane because they didn't form in our solar system. The angle isn't screaming stealth approach or deliberate survey pattern. It looks, for lack of a better term, random. So, where does mainstream astronomy stand? NASA's public-facing pages and press releases call it an interstellar comet. There's no threat to Earth. The language is cautious but clear. This is being treated as a natural object unless something drastically changes. The European Space Agency echoes that stance. Most professional astronomers I've seen comment publicly are in the comic camp, emphasizing that while the chemistry is unusual, unusual is not the same as impossible. And we've only looked at a handful of interstellar objects. Our sample size is 3. Drawing sweeping conclusions from 3 data points is like trying to determine the average height of humans by measuring 3 random people. You might get lucky, but you're probably going to be wrong. But here's where the media crosscurrents muddy the waters. Some outlets, particularly those that thrive on clicks and outrage, amplify the alien angle. Headlines scream about motherships and invasion fleets. Other outlets go the opposite direction, mocking anyone who even entertains the possibility as conspiracy theorists or attention seekers. The actual scientific middle ground, which is probably natural, but let's keep an eye on it, gets squeezed out because nuance doesn't drive engagement. Now, let's talk about fairness. The principle in science is that extraordinary claims require extraordinary evidence. Carl Schorn made that phrase famous, and it's become almost a mantra. If someone claims 3I Atlas is an alien spacecraft, the burden of proof is enormous. What would that evidence look like? Engine-like maneuvers that can't be explained by outgassing. Narrowband radio emissions at frequencies that don't occur naturally. Optical signatures consistent with manufactured surfaces. Specular reflections, panel glints, geometric structures, thermal emissions that don't match solar heating patterns. Basically, you'd need something that unambiguously screams technology. Lowe's framework is an attempt to quantify that burden. Instead of a binary, natural or alien, it's a sliding scale. The idea is that you can map observed anomalies onto a continuous score, and that score should move as new data comes in. Early on, with limited information, you might assign a higher score because uncertainty is high. As you gather more data, particularly data that fits natural models, the score should drop, and that's exactly what we've seen with 3I Atlas. The initial 6 out of 10 was based on incomplete information. The revised 4 out of 10 incorporates JWST's chemistry and the lack of observed maneuvers. If future observations show stable, predictable comet-like behavior through perihelion, the score should drop further. But there's a second axis to consider, and this is where things get philosophically interesting. The scale isn't just natural versus artificial. It's also threat versus benign. You could have an artificial object that's entirely non-threatening, a dead probe, a malfunctioning satellite from a civilization that's long extinct, a passive data collection device that has no interest in us whatsoever. Conversely, you could have a natural object like a comet on a collision course that's extremely threatening. The two axes are independent. Low scale tries to capture the artifact probability, but the public discourse often conflates that with danger, which is where dark forest talk starts to ignite, and that's a whole other conversation we'll get into later. The key takeaway here is that Loeb score is a hypothesis-generating tool, not a verdict. It's a prior in Beijing terms. You start with some probability based on available evidence, and you update as new evidence arrives. Most scientists would currently put the prior much lower than 4 out of 10. But the framework itself, the idea that we should have a systematic way to evaluate these objects, is actually pretty reasonable. We're going to see more interstellar visitors. The Vera Rubin Observatory, which is about to come online, will detect them at a rate orders of magnitude higher than current surveys. Having a common language for how weird is this one might actually be useful. So, is 3I Atlas 60% likely to be alien technology? Almost certainly not. Is it 40%? Still, probably not. But is it 0%? That's the question Lowe is asking us to take seriously. And whether you find that question provocative or pointless, it's the question that's keeping this story alive as instruments across the solar system train their gaze on a tiny distant speck hurtling past Mars tonight. Next, we need to unpack the physics that makes this object undeniably interstellar and where the mathematical cracks start to show. Part 5. The physics puzzle. How do we actually know this thing is interstellar? That's not a trivial question. Space is big, really big, and things move in complex ways under the influence of multiple gravitational fields. You can't just point at something moving fast and declare it's from another star. You need rigorous orbital mechanics, and fortunately, we have that. When you track an object across the sky over weeks or months, you're collecting position data. Each observation gives you a coordinate, right ascension and declination at a specific time. Feed enough of those observations into orbital mechanics software, and it solves for the 6 parameters that define an ellipse or hyperola: semi, major axis, eccentricity, inclination, argument of perihelion, longitude of ascending node, and time of perihelion passage. For objects bound to the Sun, the eccentricity is less than 1. The orbit is an ellipse, closed, repeating. For interstellar objects, the eccentricity is greater than 1. The orbit is a hyperola, open on both ends. The object came from infinity. It's swinging around the Sun and it's heading back to infinity. 3 Atlas has an eccentricity significantly greater than 1. There's no closed solution. This thing is not and never was gravitationally bound to our Sunday. The hyperbolic excess velocity, the speed it has relative to the Sun after you subtract out gravitational acceleration, is another smoking gun. For 3I Atlas, that excess velocity is on the order of tens of km divided by s. That's the speed it was moving through interstellar space before it encountered our solar system. No natural process within the solar system can impart that kind of velocity to an object without a close gravitational assist from a massive body. And the trajectory doesn't pass near any such body in a way that would explain it. The object arrived with that speed. It didn't gain it here. But here's where the uncertainties creep in. We can measure the current orbit with exquisite precision. We can project backward to figure out roughly where the object came from. But roughly is doing a lot of work in that sentence. The errors explode as you go back in time. Over millions of years, tiny uncertainties in the current trajectory compound into enormous positional uncertainties in the past. We can say with confidence that 3 Atlas originated in interstellar space, probably from somewhere in the general direction of the constellation it was moving from when detected. But pinpointing the exact star system not happening. The galactic velocity field is complex. Stars move. Objects get perturbed by passing stars. Trace the orbit back 1 million years, and the error cone is dozens of light years wide. Trace it back 10 million years, and it's hundreds. There's also the question of what ejected this thing in the first place. Stars don't just toss multic objects into interstellar space for fun. You need a mechanism. Gravitational scattering by giant planets during the formation of a planetary system is one option. Models show that young star systems are chaotic places with planets migrating, asteroids and comets getting flung around. Some percentage of that material achieves escape velocity and becomes interstellar. In fact, some estimates suggest there might be trillions of rogue comets and asteroids drifting between the stars in our galaxy right now, outnumbering the stars themselves. Another possibility is a close stellar encounter. If 2 stars pass within a few light years of each other, the gravitational tides can strip comets from their respective Oort clouds and send them flying. Or, in a more dramatic scenario, a star could get ejected from a star cluster, carrying some of its cometary material with it before losing it to interstellar space. Or, and this is the scenario that feeds the debris field hypothesis, something catastrophic happened. A planetary collision, a tidal disruption event where a planet wandered too close to its star and got ripped apart. A supernova shockwave from a nearby stellar explosion. Any of these could shatter a world and send the pieces hurtling outward at high speed. Now, let's talk about what happens at perihelion, which is coming up in just under a month. October 30th, 2025. At that point, 3I Atlas will be at its closest to the Sunday. About 1 point rich continue edit 4 astronomical units, roughly the distance between the Sun and Mars. Solar heating will be at maximum. If this is a natural comet, we'd expect to see an increase in outgassing activity. The sublimation rate should spike. The coma should brighten and possibly expand. If the non-gravitational acceleration we've been measuring stays low or doesn't increase proportionally with the outgassing, that strengthens the heavy nucleus model. It suggests the object is genuinely massive. and the gas production, while dramatic to our instruments, is still insufficient to significantly alter its trajectory. But perihelion could also reveal something stranger. Comets sometimes exhibit outbursts at perihelion, sudden spikes in activity that aren't smoothly correlated with solar heating. These can be caused by subsurface pockets of volatile material, suddenly breaching the surface like a pressure cooker valve releasing. If 3E Atlas has an outburst, and if that outburst happens to produce a measurable change in trajectory, we'd need to carefully model whether that change is consistent with isotropic venting, or if there's directionality that suggests structure. I'm not saying we'd find evidence of maneuvering. I'm saying we'd need to rule it out with high confidence. The JWST mass loss measurements combined with the dynamics give us that minimum mass estimate of 33 billion tons. But let's be honest about the assumptions baked into that number. It assumes the outgassing JWST measured in early August is representative of the object's average behavior over the time period used for the orbit fit. If the object is more active at some times and less active at others, the mass estimate changes. It assumes the outgassing is roughly symmetric, or at least that the asymmetries average out over a rotation. If there's a preferred jet direction that's persistently pushing in one orientation, the math changes. It assumes a certain efficiency for how ouching translates into thrust, which depends on the molecular weight of the gas and the speed at which it's ejected. Carbon dioxide and water have different molecular weights. The mix matters. So the 33 billion ton figure is a lower limit based on specific modeling choices. It's not a measurement in the same way Hubble's size limit is a measurement. It's an inference, and inferences are only as good as the models they're built on. Then there's the spin and light curve problem. If we could measure how fast this thing is rotating and what the periodicity of its brightness variations looks like, we'd learn a lot about its shape. A perfectly spherical object rotating wouldn't show brightness variations. An elongated object tumbling end over end would brighten and dim as different cross-sections face us. The amplitude of those variations tells you the axis ratio. The period tells you the spin rate. But measuring that requires high cadence photometry over extended periods, and the coma complicates everything. The brightness we see is dominated by the coma, not the nucleus. So, extracting the nucleus rotation signal from the coma noise is extraordinarily difficult. Some future observations might crack this. If the object passes in front of a background star, the occultation could give us a direct size measurement. If someone gets a radar return, which is a long shot given the distance, but not impossible, that would give us both size and spin rate. If the object's activity dies down significantly post-perihelion and we can finally see the nucleus directly, Hubble or JWST could nail the dimensions. There's a historical parallel here worth mentioning. The first interstellar visitor prompted dozens of papers trying to backtrace its origin. Where did it come from? Which star system ejected it? The best efforts using GIA data on stellar positions and motions identified a few candidate systems, but the uncertainties are massive. Over the millions of years MMUA has been traveling. Tiny perturbations from passing stars, radiation pressure, interstellar dust drag, all of these add up. The same problem applies to 3 Atlas. We can say it came from interstellar space in this general direction, but we can't say it came from Taeti, or it was ejected from the Hyades cluster. The resolution just isn't there. And then there's the jet cancellation mechanism, which deserves a plain language explanation because it's central to reconciling the weak acceleration with the strong outgassing. Imagine a comet nucleus shaped like a potato. Multiple patches on the surface are outgassing. If those patches are distributed symmetrically, and if they're all producing roughly equal thrust, the net force on the nucleus could be close to 0. It's like 4 people pushing on a car from 4 different sides, with equal strength. The car doesn't move, it just experiences stress. This is an exotic physics. We've seen it in solar system comets. Comet 67P Churyumov-Gerasimenko, which the Rosetta spacecraft orbited for 2 years, showed exactly this kind of behavior. Multiple active regions, complex jetting, but relatively modest non-gravitational acceleration because the jets mostly cancelled. So, it's plausible for 3 Atlas, but it does require a specific geometry, and it's worth noting that not all comets exhibit this. Some are dominated by a single large jet, and those do show strong acceleration. The fact that 3I Atlas seems to be in the balanced jets category is just another item on the list of things that are consistent with natural processes, but also slightly unusual. There's also a crowd science angle here that's worth celebrating. The orbital solution for 3I Atlas is built on thousands of position measurements from observatories all over the world. Professional facilities like Gemini, Subaru, and the European Southern Observatory, but also amateur astronomers with backyard telescopes contributing data to the Minor Planet Center. This is citizen science at scale. Every single observation helps refine the orbit, tighten the error bars, and constrain the models. Without that distributed network, we'd have a much fuzzier picture of what this object is doing. So, where does Act 1 leave us? The case for weird but natural is strong. The chemistry is odd but explainable. The size and mass are uncertain but not impossible. The trajectory is unambiguously interstellar. The weak acceleration, despite strong outgassing, is puzzling but could be balanced jets or high mass. Every anomaly has a plausible natural explanation, but the anomalies keep piling up, and each one individually resolvable contributes to a cumulative sense of strangeness. It's like a murder case, where every piece of evidence has an innocent explanation, but when you lay them all out on a table, the pattern starts to look suspicious. The door isn't closed, it's cracked, and light is spilling through. Next, we need to put these 3 hypotheses head to head and see which one survives contact with the data. Part 6. The Comet Hypothesis, Nature's Exotic Child. Let's start with the simplest explanation, the one that requires the fewest assumptions and fits most comfortably with what we already know about the universe. 3. Atlas is a comet. An interstellar comet, yes. An unusual comet with exotic chemistry, absolutely. But fundamentally, it's a dirty snowball. A chunk of ice and rock that formed in a protoplanetary disk around another star got ejected through gravitational interactions and has been drifting through the galaxy for millions or billions of years until it happened to pass through our neighborhood. This is the orthodox view. It's what NASA's public statements emphasize. It's what most professional astronomers default to when asked. And it's not just institutional inertia or a refusal to consider alternatives. It's based on positive evidence. JWST detected water, carbon dioxide, carbon monoxide, carbonyl sulfide, and water ice grains in the coma. This is precisely the cocktail you'd expect from a comet. These are natural volatiles, compounds that form under cold conditions in space and sublimate when heated by starlight. The spectral signatures match laboratory data for these molecules. There's no ambiguity in the identification. But let's address the elephant in the room. That 8:1 carbon dioxide to water ratio, because this is genuinely strange, and it's the detail that keeps this hypothesis from being a slam dunk. In our solar system, we've observed hundreds of comets. Most of them, when active near the Sun, show water as the dominant volatile. The typical CO2 to H2O ratio is much less than 1. You might see 1 molecule of carbon dioxide for every 10 or 20 molecules of water. Comets like C, 201, A, 2, or C, 1995001 Hail, BOP, which were extensively studied, fit this pattern. Even comets that are relatively CO2 rich rarely exceed a 1-to-1 ratio. 3I Atlas is producing 8 molecules of carbon dioxide for every molecule of water. That's not just a little off the trend. That's 6 standard deviations above the mean. In medical diagnostics, that's the difference between slightly elevated cholesterol and call an ambulance. So, we need an explanation. The formation environment hypothesis goes like this. In a protoplanetary disk, temperature decreases with distance from the star. Close in, you've got hot, rocky material. Further out, water ice starts to condense. This is called the snow line or frost line, typically a few astronomical units from the star depending on its luminosity. But keep moving outward, and you reach colder regions where more volatile ices condense. Carbon dioxide ice forms at slightly lower temperatures than water ice. Carbon monoxide, even more volatile, condenses further out. Still, if 3 Atlas formed in a region of its birth disk that was just cold enough for abundant CO2 ice, but where water was already depleted or locked into minerals, you'd get a CO2-rich composition naturally. There's precedent for this kind of compositional zoning. In our solar system, Kuiper belt objects show variations in their ice content depending on where they formed. Some are water-rich. Others have more methane or nitrogen ice. The distribution isn't uniform. Extrapolate that to another star system with a different stellar mass, a different disk temperature profile, maybe a different metallicity, and you could absolutely get conditions that favor carbon dioxide over water. The radiation processing hypothesis adds another layer. Imagine 3 Atlas has been in interstellar space for 10 million years. During that time, it's been bombarded by cosmic rays, high-energy protons, and atomic nuclei, accelerated by supernova remnants and other violent events. It's also been bathed in ultraviolet light from distant stars. This radiation penetrates the surface layers and breaks chemical bonds. Water molecules can be split into hydrogen and oxygen. Carbon dioxide can be broken down or converted to other compounds. But the radiation also creates an insulating crust, a layer of processed material that's less volatile than the pristine ice underneath. Here's the key insight. Water ice and carbon dioxide ice have different sublimation curves. Water starts outgassing significantly around 150 to 200 Kelvin. Carbon dioxide sublimates at lower temperatures around 150 Kelvin and below. If you've got a radiation-processed crust that's providing some insulation, the outer layers might warm up enough to release carbon dioxide while keeping the water locked in deeper layers. You'd see CO2 venting preferentially even though there's plenty of water inside. The nucleus is essentially a thermos bottle with a leaky cap, and the leak favors the more volatile species. This model explains why the CO2 to H2O ratio might be high now, but it also makes a prediction. As the object gets closer to the sun and the heating penetrates deeper, water should start to dominate. If we see the ratio shift toward more water activity at perihelion, that supports the radiation crust model. If the ratio stays stubbornly high, that's more consistent with a composition that's intrinsically CO2 rich. Now, let's tackle the acceleration paradox with the balanced jet solution. This is actually less exotic than it sounds. Comet nuclei are not smooth spheres. They're irregular with valleys, craters, cliffs, and plains. Some areas are covered in dust that insulates the ice underneath. Other areas have exposed ice or thin dust layers that allow sublimation. When sunlight hits these active regions, gas jets erupt, carrying dust with them. Each jet produces thrust like a tiny rocket engine. If you've got multiple jets firing from different parts of the nucleus, and if the geometry is such that the thrust vectors roughly cancel, the net acceleration is small, even though the total gas production is large. This isn't just theoretical. Rosetta's observations of Comet 67P showed this in action. The comet had multiple active regions, jets firing from the neck region and the LOEs. The net non-gravitational acceleration was present, but modest because the jets were distributed. For 3I Atlas, if the asymmetric coma JWST observed is the result of multiple jets from different locations on the nucleus, and if those jets are oriented such that their horizontal components cancel, while the vertical components produce the observed coma shape, you'd get exactly what we're seeing. High activity, dramatic coma, weak net push, the math works, the physics works. It requires a specific geometry. But comet nuclei come in all shapes and sizes. It's not implausible. But here's where we need intellectual honesty. The lower limit mass of 33 billion tons, if we take it at face value, implies a diameter of at least 5 kilometers, assuming typical cometary density. That's big. Most comets we know are smaller. The famous ones, Hall's Comet is about 15 kilometers long but only about 8 kilometers wide on average. Hale-Bopp was estimated at roughly 60 kilometers. So 5 kilometers is substantial but not unprecedented. However, finding a 5 kilometers interstellar object as only the third confirmed ISO is statistically curious. The selection effect argument goes like this. Our surveys are biased toward detecting bright objects. Brightness depends on both size and activity. A small, very active comet might be easier to spot than a large, inactive asteroid. So maybe we're just seeing the tip of the iceberg and there are tons of smaller, fainter interstellar objects that we're missing. As surveys improve, particularly when Rubin comes online, we'll start detecting those smaller objects and the size distribution will normalize. The fact that we found a big one early is just luck, good or bad, depending on your perspective. The skeptical counter is that if 5 kilometers ISOs are common enough that we've hit 1 out of 3 detections, the interstellar population must be skewed toward large objects in a way that's hard to explain. Most models of planetary system formation predict that small debris should vastly outnumber large objects. The size-frequency distribution typically follows a power law with a steep slope. Finding large objects first is possible, but it's the less likely outcome. So either our models are wrong, or our sample size is still too small to draw meaningful conclusions, or there's something unusual about the objects we're detecting. That brings us to what Mars and perihelion observations could confirm. If we see jet structure evolving predictably with solar angle, that's strong evidence for a natural comet. If the comet symmetry shifts in ways that correlate with changing illumination geometry, that's what you'd expect. If the CO2 to H2O ratio starts shifting toward more water as heating intensifies, that supports the radiation crust model. If we detect rotational periods and they're consistent with a tumbling, irregularly shaped nucleus, that's also comet-like. Conversely, if the activity stays strangely uniform regardless of solar heating, that's harder to explain naturally. If we see jet behavior that doesn't correlate with sunlight, that raises questions. If the object's brightness or spectral signature changes in ways that aren't thermally driven, that's anomalous. One more critical point, no Earth hazard. The closest 3 Atlas comes to our planet is about 270 million km in December. For context, Mars at its closest approach to Earth is about 55 million km. The Moon is roughly 400,000 kilometers away. 3. E Atlas is nowhere near a collision course. Even if it were significantly larger than estimated, even if it fragmented, the pieces would not intersect Earth's orbit. This is important because fear-mongering about doomsday comets or invasion fleets drives clicks, but does a disservice to public understanding. The risk is zero, not low, zero. So, the comet hypothesis stands on solid ground. Unusual chemistry, check. Weak non-gravitational acceleration, explainable through balanced jets or high mass. Interstellar origin consistent with ejection mechanisms we understand. Observable coma with natural volatiles confirmed. Size and mass uncertainties not yet fatal to the model. It's the simplest explanation that fits the data. But simplicity isn't the same as certainty. And there are people, serious scientists with credentials and track records, who argue we should at least consider the possibility that the numbers don't line up because we're measuring the wrong kind of object entirely. Part 7. The Mothership Hypothesis. Artifact among the stars. Now we weigh into deeper, colder water. The Mothership Hypothesis, or more generally the Artifact Hypothesis, suggests that 3 Atlas might not be a natural comet at all. It might be something built, something sent. An interstellar probe, possibly dead, possibly dormant, possibly still operational, that happens to be passing through our solar system and is doing an excellent job of mimicking a comet.